Okay.
Okay, we can start. Hello, everybody, and welcome to this seminar. Today with us we have Ivagnes. She is a PhD here at the second year, and today she will talk about enhancing non-intrusive reducer models with space-dependent aggregation methods. So, please.
Thank you, Pierre, for the introduction. Thank you, everybody, for being here today. So, yeah, today I will talk about a project in collaboration with Nicola Tonicello, who is a postdoc here at SISSA, Professor Paolo Cinnella from Sorbonne University, and Gianluigi, my advisor here at SISSA. Okay, I would like to start with a bit of motivation for this work. Most of CFD people know that in general, for computational fluid dynamics simulation, which is the application of this talk, you have to deal with very long simulations. So you have a very high number of degrees of freedom, and these simulations may last days or even weeks, even if you run the simulations on a cluster, so in parallel or in many cores. Most of the times you will have also to model PDEs, complex PDEs, Navier-Stokes equations. And so you may want to reduce the computational effort and the complexity of your problem. And in order to do so, you can rely on reduced-order models. So I think most of the people here already know what reduced-order models are. In particular, ROMs allow to express your problem in a computational, say, simple form. So you will have a system with a low number of degrees of freedom, so much smaller than the initial number of degrees of freedom. You will have much small computational time, and there are different types of reduced order models, but in our case, we work in a non-intrusive framework. So we have a purely data-driven approach, so no equations here. And I think most of reduced order models rely on this offline-online paradigm. It means that you have two steps, basically, an offline stage, which is much expensive. In this offline stage, you have to run a lot of simulations, so high-fidelity simulations, the ones that I basically introduced before. And then you can collect your snapshots that are your solutions. So in our case, the velocity, the pressure fields, for example. And then you run an online part. So the online stage is the stage which is much faster, of course, because we want to simplify our problem. And so in the online stage, we can run our reduced order model, starting from our data. Okay, so now let's start with a bit of methodology on non-intrusive reduced order models. So, okay, this is a very schematic view of how non-intrusive reduced order models work. So you have an initial manifold, which is your solution manifold. So you have your solution S, which is a function of a specific parameter, one or more parameter mu. Okay, and then you want to compute your solution for an unseen parameter. This is your problem. So what we can do is to project this manifold into a space with a reduced dimensionality. This can be done with a linear approach like DPOD, but also with non-linear approaches. And now your solutions in this space can be approximated with the reduced version. Okay, you have the reduced representations of your solution, this S tilde. And then your problem shifts to this reduced space. So you have that now you want to find this S tilde of mu star. Okay, how can we find this S tilde of mu star? With this second step, so an approximation step, this calligraphic A. And so you can use an interpolation or a regression technique, for example, and then you backmap your solution into the initial full dimensionality. And so you have your approximation S hat, which of course should be close to the ground truth, say, the exact solution. Okay, so let's start with the reduction step. So the very well-known reduction step is the POD, so the proper orthogonal decomposition. Maybe all of you already know what POD is. So basically, you start from a matrix of all your snapshots. So you have the solutions S1 and 2, S2, Sm, okay? And of course, this matrix is very, very big. So you have initial space with a number of degrees of freedom, which is high, as I said before. And so you may want to decompose this matrix. And you apply, for example, a singular value decomposition. So in this decomposition here, this matrix U contains all the discretized modes, okay? So all the discretized bases. And you can select just the first R columns of this matrix. And of course, they will be the first R discretized basis functions, okay? And this R here, of course, should be much, much smaller than the number of degrees of freedom that you have, because you want to have a low number of degrees of freedom. And you can evaluate this S tilde here, which are the modal coefficients, in this way, just multiplying UR transpose with your initial snapshots. Okay, a second approach, which is also well known today, is the autoencoder. As I said, the POD is linear, so you may want to include some linearity in your approach. And the autoencoder is a good way to do this. And in particular, it is simply a neural network that reproduces with his architecture, with his structure, the idea of decomposing and then reconstructing again your solution. Of course, it is trained such that the final output here, this S hat, is close to the initial snapshot. So it's trained, of course, with the snapshots, with the data that you have. Another third approach is a mix of the two that I said before, so the POD autoencoder. And in this case, for example, we use it if we have an initial dimension of the data, of the snapshots, that is too high to train an autoencoder. And for example, in this case, you can first decompose your initial matrix with a POD until a medium dimension, and then you can apply an autoencoder, okay? And as I said, typically you can use this approach to reduce the time of the training, or also because you cannot train the autoencoder with so high dimensionality. Okay, now let's jump to the second step, so the approximation step. So in this case, we want to find the map between this mu, so the parameter, and the reduced representation as tilde. We can have, as I said, the interpolation regression approaches. One approach can be the radial basis function interpolation. So in this case, we have this expression here, and so you will have this radial basis function. This phi is a specific kernel of the radial basis function that you can choose. And these omega I are the weights that basically are fitted to data, in the sense that they are found by solving the same equations and replacing this mu star with the mu that you have as data. Okay, second approach is a regression approach, so the Gaussian process regression. It introduces like UQ and a little bit of UQ, because it's a probabilistic framework. So here you have this normal distributed, this normal distribution here with a specific mean and covariance matrix. And also here you are free to choose the kernel for the covariance matrix that you like. This is the one that we considered, for example, in our case. And then we can have another approach that is a neural network. So of course, regression can be also done with neural networks. So simply takes as input the parameter and gives as output your reduced representation. Okay, now I want to continue by highlighting the pros and cons of all the approaches that I said. Probably you already know, but the POD, as I said, is a linear approach, but it has a very solid theory behind, and it's very fast in the applying stage. The autoencoder, on the other hand, is nonlinear, so it's more adaptable to the data that you have, but on the other hand, it's neural networks, so you are not able to understand what it's doing actually, so it's black box. And of course, you have to tune it very carefully because otherwise you can have overfitting. So there are also complexities in the autoencoder. For the approximation stage, also, for example, for the radial basis function, this approach can be very accurate and the interpolants are very smooth, but you have to carefully choose the kernel for your basis function, so it's very sensitive to the kernel that you choose. The Gaussian process regression, as I said, allows to do some UQ, so it's a probabilistic framework. It automatically tune the other parameters like the sigma and the L that were in the formulation I showed before. But for example, it's very sensitive to noise. And for the neural network, of course, there are the same, say, considerations that I said for the autoencoder. So it's nonlinear. It allows you to capture more complex relationships among data, to capture more features, but it's black box. It may need a long training and so on. So now our idea is, what if we combine all of these approaches, all of these non-intrusive reduced order models all together? And so we build the so-called aggregation method, or aggregation model. Okay, so now I would like to start with a bit of methodology, okay, theory of these aggregation methods. And I would like to start by introducing all the, say, pipe and the procedure that we followed to build our aggregation method. So first of all, the first step is to run the full order model. So as I said, in this offline stage, we should collect our snapshots, okay? And we consider these two test cases. So we have both of the test cases are flows, fast, and airfoil, okay, and are two-dimensional. But in the first case, we have as a parameter the Reynolds number, while in the second test case, first of all, we have a transonic flow. So we are close to the Mach number, and it means that there are shocks, discontinuities, and it introduces a little bit of difficulties, okay, in our model. And moreover, the parameter in this case is the angle of attack. So basically, it is the like the incidence, the inclination of the inlet velocity that you have. So I would say that this is a more challenging test case, but we will see also later. Okay, in particular, here you can see two snapshots for the first test case for the velocity field. You see that are pretty similar in the shape, say, but just rescaled if you look at the color bar, okay? But if you look here at the second test case, these two snapshots for the velocity are very different. So you see that there are differences both in the symmetry and also in the shock position. Here in the second row, in the second part of the slide, you can see the pressure coefficient trend. Okay, the pressure coefficient is like a measure of the force acting on the airfoil. And here you can see two different plots because we distinguished the forces on the upper and on the lower part of the airfoils, okay? And here you see how the pressure coefficient varies with the parameter that we have in our database. So you see that basically here they are all close. So there are not so much difference among all the snapshots. But here there is a lot of difference among all the snapshots. You see that this discontinuity here, that is exactly the shock position, varies a lot. And yeah, this introduces, of course, difficulties, complexity in the problem. Okay, so I will not go through all the details of the full order model. I'd like just to say that all these simulations are run with OpenFOAM, that is an open source software based on infinite volume discretization. Okay, and also that our full order model was validated with experimental data. Here you see just an example for the first test case. So you see the in blue the pressure coefficient that we obtained with OpenFOAM. This is another coefficient named skin friction coefficient. This second coefficient here depends on the wall shear stress, basically, so another measure of the wall shear stress. And you see that the data were validated well, fits well, okay, with the other data that we took from other papers. This one is from another reference run simulation, and this one is from a DNS. So we were happy, okay, with these results. So now that we have our full order model, we validated it, we can go on. And the second step is to divide our database into 3 parts. So we have a training part, an evaluation, we call it evaluation part, and the test set. Okay, the first step now is to train our reduced order models. Okay, and as the name says, we train this on the training dataset. And okay, we considered as fields to build our reduced order model. So as this S of mu that you saw in the first slide, we considered both one-dimensional fields acting on the airfoil, so the pressure and the wall shear stress. So basically, the field that you use to compute the pressure coefficients and the skin friction coefficient. And then two-dimensional fields, so the pressure and the velocity magnitude around the airfoil, so just like the snapshots that I showed before. Okay, these are the reduced order models that we took into account. So basically, you have both POD-based and autoencoder-based reduced order models with all the models that I introduced this way. Okay. And in particular, we replaced the autoencoder with a POD autoencoder in the case of this two-dimensional field, because the initial dimension was like 200,000, so it was too big. And to simplify all the operations, we decided to consider a POD array. Okay, now at the end of this step, we finally have our database of reduced order models. So this calligraphic chem is a set of all the non-intrusive reduced order models that depend on the reduction and the approximation step. Okay, here I just would like to show some results, some preliminary results for the reduced order models. In the first row, you see the results for the first test case and the second for the second test case. These plots are the relative errors with respect to the form, okay, for the test parameters. So here you see the Reynolds number, and here alpha, which is the angle of attack. Okay, so you see here we have these solid lines that correspond to the POD-based approaches, and these dashed lines are for the autoencoder-based approaches. We consider two different latent dimensions, so 3 and 10, very small, both of them. But if we take three modes, 3 dimensions, we see that the autoencoders, so the dashed lines that you see here, are performing better than the POD. And you see it also here. Yes, the dashed lines correspond to a smaller relative error. But if we go to 10 modes, then this is not always true. I mean, the POD have a similar accuracy with respect to the autoencoder. Moreover, I would like to underline that in this first test case, you see a trend of the error with respect to the parameter. So you see that all our models are performing better for are performing better for a higher Reynolds number, because of course the error here is smaller, but they are inaccurate for smaller Reynolds. Okay, now let's pass to the aggregation part, so to the interesting part. So we are now in the evaluation set, and we want to compute this aggregation. Okay, the idea is very simple. So it's just a convex combination of the predictions that you have. So this delta I are the predictions of all the reduced order models that you have. The eta are just the spatial coordinates and the parameter that you have, in our case Reynolds or the angle of attack. And then you have these weights. So the key problem now is to evaluate these weights that are, of course, also space dependent. And in this evaluation set, we compute the weights directly with this formula here. So you see that there is a sort of Gaussian, okay, normalized, because all the weights have to sum to 1 for each space coordinate, for each parameter, of course. And they are computed directly starting from the discrepancy between your reduced order model and your full order model. Okay, I would like to say that also a parameter that we had to carefully tune was the sigma here. And it is tuned also solving an optimization algorithm, say, so an optimization problem in order to minimize our mixed prediction here and the form solution, the corresponding form solution. Okay. So this is the procedure in the evaluation set. Now that we have our weights in the evaluation set, we may want to extend to a test set. How can we do with the regression approach? So this regression can be whatever you like. In our case, it was a random forest, but it can be I don't know, a Gaussian process regression, a neural network, also other things. And so we consider this data, the Gaussians in our evaluation validation set, and then we fit the regression and we use it to compute the Gaussians also for an unseen parameter. And finally, also in the test set, you have the same expression basically, but with this weights computed with the regression. Okay, finally some results. Okay, so this slide is to show just very quickly some relative errors with respect to the full order model in the evaluation set in the first column and the test set for this in second column. We here just show the result for one field, that was the airfoil pressure, but for all the fields more or less results were similar. So you see here in these solid columns again are the POD-based approaches, and these dashed ones are the autoencoder-based approaches. Whereas these pink and purple columns correspond to the result of the aggregation. In particular, we consider two different aggregations. One with the two best models, best measured on the training set, okay, and one with the two POD RBF and autoencoder RBF approaches, because we wanted to somehow see if combining two different reduction approaches somehow could enhance our method. Okay, so you see also the results for 3 again modes and 10 modes. I would like to underline that in the evaluation set, so this column here, you basically see that in all the cases we have an improvement, but it's by mathematical law, because we are building the weights such that our model is better than the individual ROMs. And then in the test set, it's not always true. I mean, in our case, we had quite good results, but it strongly depends on the regression performance, so on the type of regression, on how you tune it also. Okay, now I would like to focus on the second test case, which is the most challenging among the two. So here the results for a test parameter in the second test case, and for 3 as a reduced dimensionality. So here you can see in blue the full order model. So here we represent the pressure coefficient again. And in blue, you can see the full order model. In orange, here the POD RBF prediction, and here the autoencoder RBF prediction. So you see that the POD here is over diffusive, so it's not able to understand where the shock is basically. And in green, so this green shadow here are the weights. And of course, these are the weights for the POD and these for the autoencoder. So you see that basically where the POD is failing, the weights are 0. So our algorithm is understanding that the POD should be deactivated totally. And here, the weights, of course, are 1 because the autoencoder is performing better. Okay, here is just another example for 10 as a reduced dimensionality. So you see here that the POD is performing better, and in fact also the weights are not so, say, strongly differentiated among the two models that we are considering in the evaluation. Okay, these fancy graphics are for the velocity magnitude in the second test case, again for a test parameter. So you have in the first row the predictions of all the models that we have, again with just 3 modes. So you see again that the POD is over diffusive again, is not capturing the shock here, but the autoencoder, in this case, the POD autoencoder is capturing better. And then, okay, these relative errors, I would like to say that are quite high. The results are not like exceptional, but I would like to underline this fact. So the weights distribution that are very interpretable, because you see that the aggregation is activating the autoencoder in the position of the shock and in the wave, in the region of the wave. So basically when you have more nonlinearity. Okay, this is another example for the pressure field in this case, but Again, you can do similar comparisons, similar considerations. So here again, the weights are, of course, higher for the autoencoder-based approach. But in this case, I mean, there are regions like this one here, where the autoencoder, the weights for the autoencoder are lower and for the PUD are high. Okay, finally, some conclusions. I would like to say that we were able to improve the individual results for the individual reduced-order models with these aggregation methods. And of course, that our results are dependent on the regression technique that you use. And for this reason, as an outlook, we would like to test more regression approaches. And also another possible extension is to mix different turbulence models and reduced-order models, in the sense that we want to include more differentiation in our database with different turbulence models also. Okay, here you can find some references. This is the work that we just submitted last week, so you can find it on arXiv. And these two are the original, say, aggregation models that inspired our project. For all the code, basically we used this open source library. More or less everyone already know this library. It's EasyRB and it's on GitHub, it's open source. So that's it. So thank you for the attention.
Thank you. So it's question time.
Thanks for the talk. I have some concerns on the POD autoencoder.
Okay.
In general, so this is anyway a POD at the end and at the beginning of the of your reduction method. So whatever you do at the end, you just have a linear space which is given by some modes.
Yes.
So if you go, sorry, to slide 20, something like that. Before. I think you can still see these in the results. So go in the plots of the the second one. It's even clearer.
Yes.
Now the next one. You see, like in the POD autoencoder, you see after the shock there is some vertical lines in blue, very small, which are not very natural model. No, in the prediction.
In the prediction.
I think the second line is.
Okay, yes.
Is the shock that is moving.
Exactly, it's the shock that is moving. And I think this is the main problem of the POD in general, that you have these extra shocks which are coming from the different parameters, which you cannot solve if you use a POD autoencoder.
Yes, what actually we are thinking to do is to apply the autoencoder also here, so fully nonlinear, but maybe actually an idea is to reduce the dimensionality, in the sense to consider a coarser mesh and to apply a full autoencoder. That's it, that can be an idea.
Because in the 1D, the 1D quantity that you had, you didn't see this behavior. It was much better in the test that you show 2 slides before. Like a 1D is much better. Here you use just the autoencoder, right?
Yes.
Without the
yes, here the autoencoder.
It's going to be better.
Yeah, maybe we will try to use a full autoencoder also for the two-dimensional fields. Yes, maybe with a coarser mesh, then we can train it in a simple way. So.
Very nice.
Then just out of curiosity, have you tried to plot the relative error for the shear stress?
Yes, it's in the paper. I mean, I didn't put in the slide, but it's in the paper, and the results were also pretty close to the pressure one. So, yes.
So when you do PUD and autoencoder, the latent space is orthonormal or it's
Yes.
okay? It is.
In the PUD, yes. In the
No,
autoencoder, no.
Okay, so it's not.
No.
Okay.
In the autoencoder, you don't. In the PUD, yes.
Okay, I mean that's the property. And do you inform? Okay. Sorry.
No, go ahead.
Like the term, the mixed term you said, the
Yes.
the delta function. Right?
Uh,
The mixed aggregation. Like the aggregation you use.
we don't know. I mean, you don't know if it's a mix of different reducible models. So I mean, the basis in that case, you don't know if it's orthonormal or not.
Okay.
I would say no, because the autoencoder, no, you can inform your autoencoder. Also, it can be an idea to train the autoencoder such that we like did something similar last year, to train such that the bases are orthonormal.
There is already. Like,
You try to enforce somehow.
Yes.
there is a network beta variation. It's doesn't it?
Sorry?
The beta variation autoencoder, it gives orthonormal latent space, right?
Guillermo is saying yes, so I think. I don't know.
I just read, I don't know, like I never read so.
No, but you can try to enforce it, like with the particular initialization of the waves.
Just a curiosity. I mean, autoencoder are very, very better here. But how much time have you spent to train
You know, like one.
and to find the right combination
Uh,
of layer, for example, numbers?
oh,
I mean,
yeah,
the overall.
tune to tune the hyperparameters.
I imagine the training is minutes.
The training is yeah, like a matter of minutes, but to train, yeah, we spend some time. Yes, and not like a day.
Which autoencoder have you used here? Do you remember the layer?
No, it's all the autoencoders are small. Like we had 50 3 layers with 50, 20, and final dimension that you have. 50 neurons, 20 neurons, and final dimension.
Curiosity regarding the aggregation. So the slide on the yes. So the eta, I think, is the
Yes.
method. Why does it take also the? I mean, why does it take also the coordinates? And not. I mean, when you do POD, you already have discretized the space.
Yes.
So why?
Yes, but I mean, your of course, your prediction is space dependent. So yes, it's not like a parameter in the reducible model, but here the prediction is also depending on the space that you consider. Ideally, okay, you can also extend this approach to different meshes. So you can add, for example, the space dependency also in the aggregation, and then you will have also, yes, you can consider different meshes. It can be an idea also for the future.
And regarding the autoencoder, have you tried with because in your case you have the 2D problems, have you tried with convolutional 2D?
No, not yet, but maybe.
Yeah, there's continuous.
You just want to listen.
Self-promotion for that.
Thank you.
Do you truncate the POD modes? Do you truncate? Do you truncate the POD modes? Like, you have POD autoencoder, right?
In the POD autoencoder, I mean, the POD autoencoder, the medium dimension was exactly the number of snapshots that we have.
Okay.
The highest possible.
Okay.
Yes, yeah, the highest one. To include as much as non-linearity as we can, yes.
Yeah, the curiosity, at some point, I'm not sure where you showed that the error was decreasing with increasing Reynolds
With
number.
René, with Reynolds.
Which, if you have some comment on that, because I mean, from my experience, it's like the opposite side. Stay the way they are.
The easy answer is because it's relevant. If you see, I mean, have you tried to have the absolute one?
Higher value of velocity.
No,
Because here you're computing the error
But yeah,
respect to the velocity.
the velocity.
Velocity is higher.
I remember I tried a long
Yes.
time ago and changed the shape, but it's just because in one time you have 10 meters per second, in the other 100.
And also the loss is not relative loss. So you, if you train on relative loss, then maybe this will be. It's not.
Sorry.
Maybe, yeah.
I don't know.
It would
I just
depend.
I can see some of your interesting.
Yeah.
Managing normalized.
Yeah, exactly.
Mhm.
So,
Other questions? No, I think so thanks for staying.